essential tools for understanding and analyzing the structure and behavior of different kinds of networks, such as social and biological ones. They can also play a decisive role in signal processing, image segmentation, and data clustering. The crucial question, however, is how to discover such communities. And a generic answer is to define a quality function which can show the goodness of community and then applying an algorithm capable of finding communities in terms of optimizing the proposed quality function. Among many proposed metrics, one of the famous and commonly used one is modularity introduced by Newman. In a nutshell, modularity for a subset S is the subtraction of the number of edges inside S and the expected number of such edges. More precisely, think of a random graph corresponding to the given graph G to be a graph with the same set of vertices and the same degrees of G, in which edges are placed randomly. To create such a random graph, each node will be assigned with a fixed number of stub links, and then each of these two stub links will be joined at random. So let's denote this random graph by the null model of G. And in this way, the modularity of the subset S is then the number of edges within S in G minus the number of edges within S in the null model of G. So now, given a set C of K communities, we can formulate the modularity over this set as the equation shown on the slide. The goal is then to discover these communities, establishing the maximum possible values for modularity. For example, here you can see a network with two different sets of community, each of which leads to a different modularity value. It is apparent that the partitioning shown on the left side figure is much better, and on the other hand, it results in a higher modularity value. Consequently, high-value communities can be determined as one with the high value of modularity. So the immediate conclusion might be that we should somehow seek the communities leading to the maximum possible modularity value. On the other hand, since maximizing modularity lies in the NP-hard problem, most approaches considerably rely on heuristic methods. This fact has also caused insufficient research on the exact algorithms, such as mathematical programming approaches. Nevertheless, in 2008, an integer programming model for this problem was introduced. Here on the slide, you can see the standard sparse integer programming model for the modularity maximization problem. Point out that the binary variable x is defined in a way that xij equals to 0 means I and j are in the same community, and xij equals to 1 means that they do not belong in a joint community. Also note that the constraints of the model satisfy the triangle inequality. An important note is that since the linear version, which is obtained by replacing the integrity constraints by its continuous counterpart, can be solved in polynomial time, most approaches have been trying to solve the linear model first and then to use some rounding techniques to finally obtain the integer solution. Unfortunately, however, it has turned out that modularity suffers from some drawbacks. For instance, it only takes the existing links into account and does not pay attention to the missing links. In other words, modularity only measures how good the obtained communities are with respect to the number of vertices connecting to each other, while it never considered the fact that the absent links may reflect some relationship. For example, here you can see two graphs with the same number of edges and the same modularity values for a given partitioning. Nevertheless, you can easily observe that the left partitioning is much better than the right one. So relying on the modularity alone cannot help us to detect the best communities. As a result, to figure out a way for solving this problem, Chen and two of his colleagues introduced a promising extension of modularity named maximum modularity. The important insight is to try using the information obtained from the missing links to improve the modularity. For this purpose, it is known to take into account a 0-1 relation matrix U, which can specify whether there exists a relationship between two disconnected nodes or not. To be more specific, if I and j are disconnected but related, the ijth element of this matrix is 1. Now suppose that we somehow have this matrix U in our hand, and let G prime be the complemented graph of G in which there is an edge between I and G if and only if they are disconnected in G and also they are unrelated, meaning that Uij is 0. Therefore, it is natural to think of minimizing modularity in G prime while we are also trying to maximize the modularity in G. Accordingly, the maximum modularity for a given set of communities can be formulated as equation 6. The very natural question, however, is how this relation matrix is defined. Chen and his colleagues who first proposed the maximum modularity suggested that one can use expert knowledge to produce such a matrix, meaning that an expert who has superior knowledge about the network can help to provide this relation matrix. The downside, however, is that this consideration is not accurate at all, since the relation matrix strongly relies on the oracle's knowledge or feeling. From another perspective, and even more importantly, both modularity and maximum modularity, like many other community discovery methods, only utilize topological information of nodes, and naively overlooking a rich set of nodal attributes abundant in all real-life networks. So, it all motivated me to think of providing a more systematic way to define the maximum modularity relation matrix. To be more precise, I was hoping to provide a robust procedure capable of finding high-quality communities with simultaneously taking the graph topological structure and the nodal attributes into account. Finally, I came up with an idea for extracting the topological information of a graph. I applied a modularity metric to mine the communities consisting of densely connected vertices. For taking the nodes attributes into consideration, I came to utilize the graph neural network, whose ability is to use node features and the local graph structure to generate an embedding. In the following slides, utilizing the general concept of GNN feed-forward message passing, I explain an approach for extracting the information induced by the propagation of nodes properties throughout the network. Combining the modularity and novel relation matrix obtained by the design message passing procedure, I introduced to you the proposed advanced maximum modularity scheme and express it with an standard integer programming formulation. Ultimately, by solving the model using a robust approach consisting of a row column generation app procedure for solving the model's linear relaxation version and a local search technique for obtaining integer solution, we can then identify the final communities. Okay, turning our attention to finding a way to extract the graph's attributes, I had better start with reference to node embedding. Node embedding seeks to project vertices into a latent space in which geometric relation responds to relationships in the original graph. In this fashion, an encoder can be referred to as a function that maps each node U belongs to V to vector embedding ZU belongs to the space RD. Let's now raise our attention toward one of the substantial encoder models, graph neural network, which can adapt a form of neural message passing in which vector messages are exchanged between nodes and updated using neural. In each message passing iteration of a GNN, a hidden embedding corresponding to each node is updated according to information aggregated from the node's neighborhood. Informally speaking, to each node, one corresponds the so-called computational graph that accumulates the information propagated from the node's neighbor, and in turn, the message coming from these neighbors are based on the information aggregated from their respective neighborhood, and so on. Now, mathematically speaking, suppose that each node U is associated with a d-dimensional attributed vector that we represent with xu belonging to the space RD. Then the kth embedding layer corresponding to node U can be obtained by the following recursive formula. What happens is that first, the message incoming from a neighbors are summed, then the neighborhood information with node's previous embedding is combined using a linear combination, and finally, an element-wise nonlinearity is applied. Now, in order to transform the node level into something that can be implemented, we can come up with the following graph level definition of the model. However, despite the straightforward intuition behind the update procedure, considerably notable is its two limitations. The first one is the non-consideration of the attributes of each node itself. This is crucial since the effectiveness of GNN becomes severely limited as the information coming from the node's neighbors cannot be differentiated from the information propagated from the node itself. This restriction originates from the fact that self-loops are not taken into account in the adjacency matrix A. The problem, however, can be easily resolved by substituting A with A plus the identity matrix I that lets the self-loops also be involved. On the other hand, another issue with equation 8 is the non-normality of future, which can indeed lead to numerical instabilities. However, fortunately, to also prevent this shortcoming, it is sufficient to apply the symmetric normalization, meaning to replace A with A plus I with the normalization term, which is shown with the red color. Equation 9 on the slide can present the graph level expression of the model. Now, since our goal is to employ the feed-forward message passing exclusively and not to implement the backpropagation procedure, training the weight matrix W is not specifically a part of our requirements. Instead, the only thing that matters to us is finding a final vector representation for each node, by which we can sufficiently reflect the similarities among nodes with respect to the information originated or propagates from attributes. For this reason, by omitting W, we get the following embedding matrix H. One important insight that could be gained is that GNN feed-forward message passing is able to effectively encode neighborhood information in such a way that after performing the updating procedure for a number of layers, similar nodes in graph will tend to have an analogous final embedding representation. This is primarily due to the fact that each node inherits the information or attributes from its neighborhood. Accordingly, any technique for computing the distance between each pair of final vector representation can naturally lead to obtaining similarities between the corresponding vertices with respect to their attributes, of course. In this work, I employed the Z-normalized Euclidean distance to measure the similarities between nodes. More precisely, given two nodes I and j with the corresponding vector embedding hi and hj at layer k, equation 11 can determine the distance between I and j. It is not difficult to check that for every pair of nodes I and j, x star ij belongs to the closed interval 0 and 1, and that it preserves the triangle inequality. Substantially, x star forms a metric space, which we denote by ed on graph G. Clearly, the larger the obtained ed value between two nodes, the less similarity between them. So, as already mentioned, the larger the x star is, the less likely it is that I and j are similar. That is, the less correlated they are, and therefore the more likely they are to be in the distinct communities. This intuition, and also the fact that modularity maximization problem can be nicely expressed for weighted graphs, persuaded me to propose an advanced maximum modularity model by recharacterizing the relation matrix and so the complemented weighted graph G prime using ED. Accordingly, we can define the relation matrix A prime and G prime as follows. Given a relation matrix and noticing that the induced metric ED constrains the modularity maximization model guarantee the triangle inequality, the advanced maximum modularity problem can be formulated as the following IP. Point out that the fractional optimal solution to the linear version of the problem provides us with a metric space where the distance between every pair of nodes is at mass 1. So let's call this metric as the LP distance. The more the LP distance between two nodes, the less tendency they have to be in a shared community. Considerably important is the fact that maximizing IP model of the proposed advanced maximum modularity coincides with the simultaneously maximizing the modularity over the original graph G and minimizing the modularity over the complemented graph G prime obtained by the proposed message passing approach. Whereas the first component makes sure to retain communities, each consisting of a densely connected nodes, the latter attempts to extract the communities containing vertices with the most similar attributes possible. Okay, now that we have the model ready, we can discuss an approach for solving the model and discovering the communities. Efficiently solving IP model consists of two main parts: solving the linear relaxation model and accurately drawing the obtained fractional solution to the integer one. The first step of the solution approach is to optimally solve the linear model of the problem, and particularly promising is that this could be efficiently solved by employing a row and column generation technique. So the remaining step is to find a way to round the fractional solution into integer ones in order to discover communities. For doing this, I employ the local surrounding technique, which works in the following way. First of all, we let the so-called center point represents each community. So we randomly choose several vertices and let them be our initial centers and isolated communities. After that, a repeatable procedure takes place in which first a local search move will be selected for adding or deleting centers. Then each center node J assigns to a community whose center node has the minimum LP distance to J. So the algorithm starts working and terminates when no improvement local search move exists. So in the following slide, by providing several experiments, I try to show how the proposed model can outperform the other approaches. The following table shows the network used for this experiment. A significant common factor among this network is that the optimal communities for all of them are available. This fact further helps us to make a fair comparison. More precisely, I employed two famous performance normalized mutual information and adjusted random index, which can ideally measure the similarities between two partitioning of a network. We can perfectly use these metrics to measure the similarity between the communities obtained by an algorithm and the optimal set of communities. In brief, the more the NMI and ARI value, the more similarity between the obtained communities and the optimal ones. This slide provides a comprehensive comparison between the proposed method and some state-of-the-art algorithm. As it is apparent by the NMI and ARI ranks, the proposed method significantly outperforms other algorithms in the sense that the communities it discovers are much more similar to the ground truths than those obtained by the other methods. Although the results obtained in this figure perfectly illustrate the proposed method's superiority against some other state-of-the-art algorithms, it could still be worth investigating the role of applied GNN feed-forward message passing procedure in improving the communities. For doing this, we compute the value of NMI and ARI associated with each of the network's obtained final community in terms of the different hidden layer number K. In this regard, K equals to 0 refers to the case when only modularity is employed to identify communities with respect to the graph topological structure. Figure on the slide shows the result. It is clear that, first of all, maximizing the modularity alone, meaning that only relying on topological aspect and ignoring the nodal attributes, cannot lead to promising results. Furthermore, considerably notable is the approving effect of increasing the number of hidden layers. The more the value of K, the more accurate the embedding vector representation becomes due to the more information diffused through the neighboring vertices. However, interestingly enough, for a certain point on, increasing K does not influence the quality of community, and this is primarily due to the fact that after a certain number of updates, each of the embedding vectors starts to converge. So, all right, to conclude, I built a community discovery method on the basis of the mathematical programming formulation and the graph neural network feed-forward message passing manner. I managed to propose a systematic way to generate an accurate relation matrix for the maximum modularity problem, centered on an efficient node embedding technique, which enabled us to model the standard integer model for the maximum modularity maximization problem. A successful row column generation technique and a local search-based rounding algorithm facilitated us in solving the model accurately and computing capturing the communities of a given attributed network. Furthermore, the proposed computational experiments showed that our results highly resemble the optimal solution and that our algorithm outperforms the previous well-known algorithm. So that was all. Thank you very much for your attention.
Thank you very much for your interesting presentation, and I will start now the discussion session. If you have any question, please ask now or write on our chat. Is there any question?
Yes, I have a short question. Is it possible to use your solution for clustering mobile networks where the connection is dynamically changed?
Yeah, okay. It's a very, very interesting question. So first of all, let me say that working on a dynamic network is a bit more challenging because it is always changing. And so far, I have not found a proper way to generate my approach so that it can somehow apply to this kind of network. But the interesting thing is that it is one of my goals now, and I am really trying to somehow adapt this algorithm to work for these dynamic networks. It is actually my hope.
Yes.
But so far, I do not know how to implement or how to generate this model to work on this kind of networks.
I wish you successes on this area. Thank you very
Yes,
much.
you're welcome. You're welcome. Thank you.